Okay, so we got our two elements in there. Let's put in an elbow in this model. Before I put in the rest of the model, let's just take a look at the elbow by itself. We're going to build a stiffness matrix for a 2D bend element. We're going to build our local flexibility matrix for this system. It's kind of an interesting point. The elbow was defined originally in the Mare Island program, flexibility method, and the piping codes reference a flexibility factor. So we are still using a flexibility matrix initially in Caesar 2. Then we'll invert it to make it a stiffness matrix to use with the rest of the components. But the flexibility method was the predecessor of the stiffness method that we're using today. Generate the flexibility matrix, check it against Caesar 2. Then we're going to invert it and create a stiffness matrix into it. We're going to put an anchor on it and then run it in Caesar 2. The model that we're going to use is called bend. Let's take a look at the MathCAD work for this. One note here, if you're running this on Caesar 2 along with me, there's a configuration switch called bend axial shape factor. Turn that to false for this exercise. I don't recommend you turn it off for running Caesar 2, but it kept my math a little simpler here today, and we're trying to get the concept across, not the specifics. It's a minor change in the numbers, but if you notice a difference in your numbers, it might be because of this flag in the program. Here's the same data that we calculated before. My elbow will be a 90-degree elbow, so my angle theta will be pi over 2, 90 degrees, pi over 2 radians. Here's that shear term that we have for our elbows from ANSYS, and there's our phi term. We saw that before. Now, we need this flexibility factor from the piping code. B31.3 Appendix D gives us a flexibility characteristic. The wall thickness of the pipe times the bend radius divided by the mean radius of the pipe squared. That's the flexibility characteristic. The flexibility factor is 1.65 divided by that value. So there's our flexibility factor. That means this pipe is, in bending, as flexible as a straight run of the same arc of this bend that's 5 times longer. Here's a definition of the flexibility factor. The flexibility factor is the length of straight pipe having the same flexibility as the component divided by the centerline length of the component. That's from the ASME Companion Guide, Volume 1. Here are the terms that we're going to use to calculate the flexibility matrix of this element. We're going to use this coordinate system, A, B, and C. This is right out of the Mare Island program in developing elbow flexibilities. It's a 3x3 flexibility matrix. Now this is with this local ABC axis. I want to convert it to my global coordinate system that I was using in the previous examples, X, Y, Z, RZ. And here's my converted flexibility matrix for this elbow. When I populate these terms in the flexibility matrix right there, the A matrix, I can say deflection equals flexibility times load. So if I start putting on different types of loads, I can see if this matrix matches Caesar 2 in results. I want to know what the deflection is. Put in 10,000 newtons, and how does it deflect? That's in the X direction. Then I put on 10,000 newtons in the lateral direction. How much does it deflect? And then finally, I put a rotation of moment on the far end, and it says 10 to the 7th. In Caesar 2, our input will be in Newton meters, but we're using Newton millimeters here, so I will just take that number. I'm going to put in 10,000 in Caesar 2, but it's 10 to the 7th here. All right, so again, I have developed a flexibility matrix using these terms. I converted it to my coordinate system. And you don't have to drop in an anchor with this flexibility method. It's a relative term, flexibility from one end to the other. So then I put on my test loads, X, Y, and Z, and then see what Caesar 2 says. So now when I put on my loads, my deflection for the first load, I want to see 0.1256, negative 0.1646, and then the rotation at 0.665 degrees. This is radians, that's degrees. So 12556 minus 1646, 0665. Same numbers. When I put on the second load, I want to see minus 1646, 2586, and 11654, 1165. And then the rotation, I want to see minus 1.161, 2.034, and 1.2009. We'll start that in Caesar 2 and compare those. I'm going to open up the model called bend. Look at the input of that. Now, one thing in Caesar 2 is that when I put on this bend, I just have a pure bend. Again, 10 to 20 is the vertical run, and 20 will end up rolling out to be the far point over here. This is no 20 as far as I'm concerned. When I look at my input, though, I had to go 20 to 30. So 20 and 30, this is exactly the bend radius, 152.4 millimeters. So 20 and 30 are at the same point in space. But Caesar 2 requires that there be a little bit of length on this element, this little bit of 20 to 30. And you can control that in the configuration file as well. I dropped that add-on of false of 5%. I put it at 0.5% of added length on that run. Let's take a quick look at that. I'll look at my configuration file. Here's my configuration file, and here's my units file that I'm using. The two switches that we have worked with, here's that bend axial shape switch. I turned to the false. See, it's bolded. That means it's not the default setting. These are bolded because these are in metric units now. The other switch, bend length attachment percent, 0.01%. So there's very little added length between nodes 20 and 30. And of course, we always think of 20 and 30 being coincident when we look at Caesar 2. I have built my model. I put my loads on the end. Here's my forces. 10,000 in the x direction is my first vector. 10,000 in the y direction, that's my second vector. And my third vector is 10,000 Newton meters, which is 10 to the 4th Newton meters, but 10 to the 7th Newton millimeters. Do my error check. And look at my load cases. Look at each one of those four sets individually, run that analysis. And I'm going to look at the deflections for those three load cases. And you can compare these then with what we have in our MathCAD worksheet. I want to see node 20, those three numbers. 0.126, minus 0.165, and minus 0.0665. We can reproduce the elbow in terms of a flexibility matrix. Our next step is then to go on and take a look at it in terms of a stiffness matrix.